All right. Thursday. May 13th. Pretty exciting stuff. What are we doing today? Doing the derivatives. All right. So just going to do derivatives all day. All right. So an hour's worth, half hour's worth, kind of see what happens. And we're just going to go through and we're going to get them. All right. As many as we can. I think I got about, I don't know, 50 or so on the board here. So I'm just going to kind of go through all of our rules here. We're going to focus on, this is for this exercise, these exercises, we have basic, in theory, we should have all of the derivative rules under our belt, okay? Meaning that we've got chain rule is up for grabs. We've got, product rule, quotient rule, natural log, different things like that. There's no arc, actually, there's no arc tangents or arc sines or hyperbolics either, okay? But so it's kind of like it's like this is the lesson that you would have before you get into the, derivatives of tangents and the arc tangents, okay? All right, so basically here, let's go ahead. Let's cut to the chase, shall we? First is a of x is negative 4e to the negative 2. Oh, hold on a second. I messed this one up already. There should probably be, I was probably, hey, let's pretend like this is what it is. What's the derivative of this? 0. How's that sound, huh? A prime of x. Why? Because there's no x's in there. Look at that. I probably had a typo and I forgot to put an x there. Okay. So we'll leave it like that. All right. Now, over here, we've got 16 times 16 to the x. Okay. This is going to be our power rule. Okay. And it's going to look a little bit like, let's see. We're going to write b prime of x. The 16 stays, constant multiple rule right there. The power rule, I said power rule, I meant exponent rule. This is 16 to the x, okay? The exponent rule works like that. But then it's the natural log of the base, okay? So there we have it, 16 times 16x, and so forth, natural log of 16. All right, there's that one. Here's one. Oh, I always like to put these on tests very close to each other. Look at that, 16x to the 16th. And then here I put 16 times 16x. Just to remind students that, hey, the exponent rule and the power rule are different. All right. So here we got this one. All right. Oh, something happened. Funny light flash. So c prime of x here is, let me move that guy down, is 16 because of the constant multiple rule, okay, times another 16 because of the power rule, times x to the, what do we do with this 16? We're going to lower it by 1 according to the power rule. Okay, remember, you lower these guys by 1. All right, so it's 15. Okay, here now we're starting to get into some fancy chain rule. This is going to be a chain rule here. All right, so it's d prime to the x of x, sorry, e. Now this is a funny one because a lot of students might think, ah, this is e because it's a power or not a power, but an exponential function. So I'm going to have to use the exponential rule because exponential e kind of always shows up, you know, but it's not. This is actually just a constant. Okay, so this is a constant. Now I've got the power rule of 2 cosine x to the 1. Okay, so what happened there? This is actually, remember, this could be rethought of as e cosine x squared, which case we have a power rule. So the 2 moves to the front. It gets lowered from a 2 to a 1, and I rewrite what's there. And now I chain rule myself out of this, and I multiply onto the end, chain onto the end, the derivative of the thing that I rewrote. This is a classic chain rule, right? So there we have it. And the derivative of cosine is negative sine. You'll want to remember that one. So that was pretty exciting one there. Okay, let's talk about this one. Oh my, look at this. This is a wild one. We're going to need a lot of space for this one. So it looks like I got the sum of 2 functions, right? So we know that the derivative is the sum of the derivatives. So I'm going to end up having some different various things going on here, okay? So let's go with, I don't know. Let's go with, let's just go with the first one here. This is going to be a product rule. And it's going to work out such that I'm going to take the derivative of the first function. So 4x to the third, that was just a power rule, right? Then I don't differentiate this thing, e to the 2x. Okay, so then I multiply it by e to the 2x. Okay, plus the 4 to the x not differentiated. Sorry, I said 4 to the x, I meant x to the 4th, times e to the 2x differentiated, right? But e to the 2x differentiated is actually just, what is it? It's e to the 2x times 2, because it's, remember, the derivative of a power of an exponential function is you rewrite the as it is, and then you multiply by the derivative of the exponent position. Okay, so the derivative of e2x is 2. And then you also would need to multiply by the natural log of e, but we all know that that's 1. And so we're done there. Okay, so that's that one. Now, this guy here is going to have its own derivative. All right, so that's just going to be 3 to the x squared times e to the negative 4x plus 1. Plus, this is again a product rule, right? So I took the derivative of x to the third, okay? And I'm multiplying it by this guy, not differentiated. Now I add x to the third, not differentiated. And then I multiply by the derivative of e to the negative 4x plus 1. Negative 4x plus 1. So that's times, I guess it's just going to be a negative 4. Okay. And yeah, we leave it like that. You can factor some things out, do some various things here, but clean it up. This, maybe move this 2 into the front there. Excuse me. But in the end, that's what you're looking at. That's a pretty nice derivative. Let's see what else we've got here. Oh, look at this guy. G. All right, so this is g prime of x is the derivative of this thing. Okay, so let's take a quick look at this. Looks like I've got 3 to the, I've got 3 to the x or 3 to the, actually, it looks like an entire quadratic formula or function here. So I've got 3 to the quadratic something minus 2e sine x. So I'm going to have 2 exponent rules here, okay? And we're going to notice the difference. So it's got 3 to the 3x squared minus 2x plus 1 times the derivative of the exponent position, which is going to be 6x minus 2. Okay, so and this is not in the exponent position. This should be down at the same level as the 3. Okay, and that guy is differentiated. We do have to multiply this by the natural log of the base. So we're going to write natural log of 3 there. Okay. Now I'm going to subtract this derivative. I'm going to subtract this derivative. So it's equal to 2e to the sine x times the derivative of the exponent or sine x. So that's just going to be cosine x. Now, you can multiply this by the natural log of e as well, but again, that's 1, so you don't need to write it. One mistake that people would make is they would write the natural log of 2e here, thinking that this is the entire sort of base of my exponential expression there, but it is not the case. Okay, so don't fall for that trick. Okay, so this is not correct. This is not necessary. All right. So there, we've got ourselves the derivative. All right. So that was that one there. All right. Let's see what else we've got today. Here we go. Terribly sorry. Sorry about that. H of x equals 3 log base 3 of x minus 1. Okay. And let's see. Our log was it had a natural log of the base in the bottom, right? So this is h of x. So this is 3, right? And you can kind of, in a way, the way that I think of these logs, right? Because I always forget this rule, actually, honestly speaking. So I kind of think of this as, I do this as a change of base. I do it as the natural log of x over the natural log of 3, okay? Because I can use that change of base formula. Log base 3 of x can be rewritten as natural log of x times the natural over the natural log of 3. Okay. And then the derivative of the natural log of x is 1 over x. Okay. Whereas this natural log of 3 actually just becomes a constant. And so it's the natural log of 3. And so, yes, that's what I was saying. It has a natural log in the base. All right. So let's roll through this one. So we've got 3, constant multiple rule. The derivative of log 3x is 1 over, I guess I'll write it as x ln 3, okay? And I'll minus a 0 because the derivative of 1 is 0, all right? So you'll want to remember these log derivatives here. And again, it has to do with the change of base formula and then taking the derivative of the natural log of x, which and most people are a little bit more familiar with that being 1 over x. Okay. You don't need this 0 here, obviously. I think you could kind of figure that out. So, oh, I forgot to write my prime. I probably forgot my prime on several of these. No, G prime, F prime. Oh, okay, I've been doing pretty good. Now I've got J prime. All right, J prime. J prime sounds like a nice band or something like you can do. Anyway, derivative of x is 1 minus, then I've got 2, right? Now, we can look at this a couple of different ways. I'm actually not going to differentiate this yet. I'm going to rewrite it. It's a good thing I've got an eraser. I'm going to write this as x minus 2 tan to the negative 2x. Okay. So all I did there is I moved my tan up to the top. Okay. And then I changed it to a negative exponent. What this is going to allow me to do is use the power rule instead of having to use some kind of like quotient rule of some sort, right? And so it's going to end up working out really nicely. Okay, so I've got now j prime of x is derivative of x is 1 minus 2. Now this is going to be a chain rule, this tan here. Okay, so I'm going to write this as a negative 2 tan to the negative 3. Okay, I lowered my thing and I replaced my tan x in there. And now I have to multiply, according to the chain rule, by the tan x, derivative of tan x, which is secant squared x. And so that's our thing there. Now I've made a slight error here. Notice I've put this minus sign here without, notice these should have been multiplied together. This negative 2, I put it out here. So I would probably want to put like a little dot in there, or be a little bit more clear and change this negative 2 to a positive 4 or something like that, right? And then I can maybe clean this up, do secant squared x over tan to the third x, and this is 1 out there, okay? But again, like for example, on the AP test or like on a test where basically they just ask you to find the derivative and that's it. Oftentimes, I would say most teachers I've come across, and myself as well included, I don't require you to simplify. Notice I haven't simplified any of these derivatives up in here, right? I just kind of leave them as they are, because at this stage in the game, we're really kind of testing students on whether or not they can successfully maneuver themselves through a derivative, and not whether or not they can simplify the derivative after they've gotten it, right? Because that's, something that we would test at different times or things like that. So again, I'm just kind of going through these derivatives while not simplifying them. Okay. So what else do we have here? Here's a couple of more functions. All right. All sorts of functions here. So k of x. Let's see, do I want to differentiate this right away? I sure do. Okay, cool. So I'm going to do equals 1 over, right? The, so remember, the derivative of the natural log is 1 over the thing that we have written here. So this, right? 2x squared minus 5e to the x, okay? But now this is again a chain rule, because now we have to multiply by the derivative of this thing here, okay? So, because the derivative of natural log is 1 over x, but in our case, we're kind of like doing a chain rule. So let's see, I'm now taking a 4x minus, oh, look, it's just 5e to the x, 5e to the x. Derivative of 5e to the x is 5e to the x. Probably want to put that in a parenthesis like that, so that it's not mistaken as being the 5e to the x hanging out at the end. If I hadn't placed that parenthesis there, it would have been construed as an error, because it would have been maybe, okay, I can pull the 4x up into here, but then this negative 5e to the x would have stayed down, and that would not be the correct derivative, okay? A lot of students and professors and everybody write natural log derivatives like this. They just rewrite the bottom, so 2x squared minus 5e to the x, okay? And then they write their derivative automatically in the numerator position. So 4x minus 5e to the x. And that's going to end up being your derivative there, okay? This one looks wild. I got a bunch of pies in here. What was I thinking? All right. So let's see here. I'm going to do some crazy stuff here. Oh, my. look it, I don't like the way this is written. So I'm going to change this. This is going to go L of X, right? This is an L. I don't want to make it into a 1. So I'll write my L's like this. L of X, okay, is, let's see. We know that pi to the X is, but it's to the pith root. Who thought of this? I don't know who did this. So I'm going to rewrite this as pi to the X over pi. I don't know if you can see that. I'll write it a little bigger. 1 over pi to the X. But remember, pi root would be over pi. Okay. And then not only that, I'm actually going to bring this out of the denominator into the numerator. So I'm going to rewrite it again as a pi to the negative X over pi. And now this is what I'm going to do. I'm going to take the derivative of this guy. Okay. Now, it looks like I got an exponent rule because my X is in the exponent position. So my derivative is the same thing, okay, written. So pi to the negative X over pi, okay, times the natural log of the base times the derivative of the exponent position, which is a negative 1 over pi. Okay. I'll put some parentheses around that. Yeah, because the derivative of negative X over pi is 1 over pi. Derivative of any exponential function is you rewrite it as is. So I rewrote it. You multiply it by the natural log of the base, and you multiply it by the derivative of the exponent position. Chain rule. Right there. That was. Let's see what else we've got. Some crazy stuff there. All right. Let's see. All right, let's see. We got 1 over x minus 2 over secant x over x. Okay, now, a couple of ways we can look at this, all right? You could think of this as a quotient rule, all right? Immediately. But I'm kind of thinking it might be nice for us to simplify this first, okay? So basically, I can write m of x as 1 over x, right? Minus 2 over secant x over x, okay? You can split that denominator out. Now, this is kind of like that. So you kind of now, you have yourself some complex fractions here. And so it's 1 over x over 1. So I can multiply by the reciprocal. So it actually becomes 1 over x squared minus 2 secant. And so this is going to be 2 over x secant x. All right. Now, the reason why I did that is now I've got basically 2 separate integrals that I can do, derivatives that I can do there. All right. So the derivative of 1 over x squared, m prime of x, is going to be a negative 1 over x to the third. Everybody kind of hopefully remembers that one because it's a negative 2 in the exponent position. I got I forgot my 2. Actually, I'm glad I stopped to explain it to y'all. I would have missed that one there. Because it's a negative, you can kind of imagine this as a negative 2x. So I move the negative 2 down, and then I take the 2 and lower it to a negative 3, and therefore ends up being a 3 in the denominator. This one is 2x secant x. Now, a couple of ways of looking at this. Do I want to use a quotient rule, or do I want to take this and move it into the top and give it a -1 exponent? I think I'm going to do it that way. All right. Which if I'm going to do that, I'm going to rewrite it as a 2 to the x secant x to the -1. But right now I've got on the page incorrect stuff. Because look at what I did. I took the derivative of this, but I didn't take the derivative of this section. I only rewrote it. So, but over here, I've clearly stated that this is the derivative, everybody, but it's not yet the derivative. So this, either I have to make some major changes here, or I have to undifferentiate this and rewrite it as maybe I can even write it like that. How about I'll do that? And now I haven't differentiated yet. Okay, so I'm going to erase that derivative symbol. And now I'm going to attempt to differentiate. So how does that look? So now again, this is a -2x to the -3, which becomes what we had before. Now this one is going to be a little easier to differentiate because it's a -1. It moves down, so it times this 2. So I'm actually going to get a +4 there. No, 2. I don't know what I was thinking there. +2, because this -1 moves down. I open up a parentheses and I move this -1 down to a -2. Why did I open such a large parentheses? Because this is a product rule now. So I'm going to open up a large parenthesis. So derivative of secant is secant tangent. So this is a product rule. I'm going to take the derivative of x, so 1, and then I'm going to rewrite secant x. I'm going to add the derivative of x not differentiated, and now I'm going to differentiate by secant. I'm going to take the derivative of secant, so it's secant x tangent x. Okay, and this is raised to the -2 power because again that outer thing was a product rule. Sorry, power rule. Okay. Let's see here. Am I going to have enough space for this guy? I might have to go out to the left here or to the right. This one looks wild. Can I do something like this? I'm going to x, and I'm going to paste him over here. There's a nice little friendly space for us. Okay, so this one looks pretty challenging, and I'm going to take a look at it. Now, I've got the natural log of tangent of x with an x over here and a square. My gosh. So I think I'm going to use the quotient rule this time. I'm going to go for it. I'm going to go quotient rule. So I'm going to set this up. When I set up a quotient rule like this, this is a wild quotient rule. So because there's all sorts of chain rules and product rules and things like that inside the quotient rule. So I'm going to say my numerator is 6x minus 1 squared, okay? And my derivative of my numerator is a 2 times 6x minus 1 to the 1 times 6, okay? Then I'm going to set up my denominator as well, which I guess I'll write it right here. My denominator is x times the natural log of tan x squared. All right. So now my derivative is, I've got a product rule overall here. I've got one little mini function, x, hanging out here. And then I've got another like multifaceted 4-function sort of thing here. No, natural log, tangent. No, there are only 3 functions here. Natural log, a tangent, and a power. So this is going to be a double chain rule here. Okay. So I have to take the derivative of x, and I have to take the derivative of this, and then I have to use this in the product rule. So remember, the product rule says I leave one and I differentiate the other. So I'm going to differentiate the x, so I'll get a 1. Then I'm going to leave this thing here. So the natural log of tangent of x squared. And then I add the other one not differentiated. So therefore the x is not differentiated. And now I multiply by the derivative of this monstrosity over here, which is just going to be a 2, because my outer function is a power rule. Move the 2 down. Okay. Then I open up a parenthesis and I rewrite. So natural log of tan x to the 1. Okay. And I didn't have to write that one. Now I multiply by, according to the chain rule, the stuff that's in there, but differentiated. So I need to multiply by the natural log of tan x, which is 1. The derivative of that is 1 over tan x times the derivative of tan x, which is secant squared x. Secant squared x. All right. And then I can close out my parenthesis here. All right. That was a wild power rule here, then a natural log rule, and then a trigonometry rule right there. Okay. Now I haven't even taken the derivative of n. So n prime, right, is going to be, remember what is it? The quotient rule. The quotient rule means it's the numerator differentiated. So it's, oh, I've got an ends over here. I used ends too many times. Shoot, that's an n. That's an n. I'll call this a. How about I call this a, and I'll call that a prime. You see what I did there? I did numerator and denominator, but the function is actually called n, so I don't want to do that. That would have caused a little bit of clash in my variables. Okay, so here what we're going to do is we're going to take the numerator differentiated, so a prime times d, okay, minus d prime times a over d squared. Okay. Now I'm going to have to write all that stuff out, right? So that's a pretty wild little thing. I don't really have much space. So, we can kind of, take it. Oh, I'm going to try this. This is going to be fun. I'm going to grab a prime. And I'm going to move it in there. Oh, there it is. Right. Perfect. Okay. Then I'll multiply by d, right? D is over here. Oh, I missed my 2, right? Didn't work out perfectly. Now I'll multiply by d. Look at this. This is going to be fun. All right. Multiply by d. All right. Okay. And then I'm going to subtract d prime, which is this whole giant thing here. So I'll grab that whole thing. This is going to be exciting. This is why I wanted to do this, actually. Look at all that. Wow, I can get all of this. Put it here. There we go. Okay. And that's a 1 there. And then I have to multiply it by, oops, I missed my parenthesis. Then I have to multiply it by a, which is this guy here. So I'll grab that guy. Oh, he has to go way out on the edge there. Oh, can I do it? Can I do it? I can. Awesome. So there's that one. So there's my numerator. So it's crazy. a prime d minus d prime a all over d squared. Okay, so I'll make a big thing. Over d squared is going to be this thing. So it's going to be x natural log of tan x squared, all of that squared. There's that one. It's a bit of a bear. I can't believe I put that on this thing, but there we have it. Okay. So that was a whole whack of derivatives that were pretty fun. Hope you enjoyed watching it. I know I had a good time. And so, yeah, I guess I'll sign off. All right. Boom.